Hello everyone. In the last lesson, we explored the close relationship between materials and water. Today, let's shift our perspective and talk about the story between materials and heat. Why does an iron handrail feel extremely cold in winter, while a wooden handrail feels warm? Why is double-glazed glass more thermally insulating than single-glazed glass? Behind these phenomena lie the thermal properties of civil engineering materials. First, let's look at thermal conductivity. Thermal conductivity, simply put, is the ability of a material to conduct heat. We express it using the thermal conductivity coefficient. A strict definition is, when the temperature difference between the two sides of a material is 1 K 1 degree Celsius, the amount of heat conducted through the material of unit area and unit thickness in unit time. You only need to remember one rule. The larger the thermal conductivity coefficient, the faster heat transfers, meaning the material conducts heat easily, for example, metals. Conversely, the smaller the thermal conductivity coefficient, the better the thermal insulation. Heat has difficulty passing through, for example, foam plastic. Besides transferring heat, materials can also store heat. This is heat capacity. Heat capacity refers to the ability of a material to absorb heat when heated and release heat when cooled. Its magnitude is measured by specific heat capacity. The larger the specific heat capacity, the more heat the material can store. What is the difference between thermal conductivity and heat capacity? Let's use two real-life examples. Example 1. Thermal conductivity. In the past, ice cream sellers on the street used foam boxes to store ice cream. Or, because foam has very low thermal conductivity, external heat can hardly penetrate the box, so the ice cream does not melt. Example 2. Heat capacity. In winter, we like to use hot water bags because water stays warm for a long time. But if you heat a large iron block and hold it, you'll find it cools down quickly. This shows that water has a large heat capacity, good at storing heat, while iron has a small heat capacity, poor at storing heat. Now let's look at this table of thermal properties of common civil engineering materials. Here are several typical materials. Steel, very large thermal conductivity coefficient, very small specific heat capacity. It is impatient, transfers heat fast, loses heat fast, and cannot store heat. Air, extremely small thermal conductivity coefficient. This explains why sweaters and down quilts keep you warm. These porous materials contain large amounts of still air, which can block heat loss. Water, the largest specific heat capacity. Water is a super warehouse of heat. Raising or lowering its temperature by 1 degree requires absorbing or releasing a huge amount of heat. That's why in summer, even under strong sunlight, pond water remains cool, because water heats up very slowly. Now let's have a short class discussion. Why does double-glazed glass have good thermal insulation performance? Which thermal property of materials does it use? In fact, the key structure of double-glazed glass is the gap between the two panes, which is filled with dry air. As we just learned, air has a very low thermal conductivity coefficient. It is very difficult for heat to pass through this air layer, which cuts off the path of heat transfer. Therefore, double-glazed glass achieves insulation by using the low thermal conductivity of air. Besides heat transfer and heat storage, materials also change in size when temperature changes. The common thermal expansion and contraction, professionally called thermal deformation. It is usually expressed by the linear expansion coefficient. Do you remember the best partners we mentioned in Chapter 1? One key reason why steel and concrete can work together is that their linear expansion coefficients are very close. This means that when subjected to temperature changes, they can expand and contract simultaneously, moving forward and backward as one, without damage caused by inconsistent deformation. Finally, Let's talk about a property closely related to safety, fire resistance. It refers to the ability of a material to resist flame and high temperature. According to fire resistance, civil engineering materials are divided into 4 categories. 1. Non-combustible materials. Do not ignite, do not carbonize, do not support combustion. Remain unchanged no matter how heated, for example, stone, concrete. 2. Low combustible materials. Difficult to ignite, difficult to carbonize. May be damaged but very hard to burn, for example, fire retardant treated wood. 3. Combustible materials. Can burn and continue to burn after the fire source is removed, for example, ordinary wood. 4. Flammable materials. Ignite immediately and spread fire rapidly. You may remember the high-rise apartment fire on Jiaozhou Road, Jing'an District, Shanghai. The illegal use of flammable materials such as nylon nets and polyurethane foam was the main reason the fire quickly got out of control and caused heavy casualties. Alright, let's summarize. Today we learned the thermal properties of materials. Thermal conductivity, ability to transfer heat, heat capacity, ability to store heat, thermal deformation, thermal expansion and contraction, and fire resistance, fireproof ability. Mastering these properties helps us better solve problems of thermal insulation, heat protection, and fire safety in design. We have finished the physical properties of civil engineering materials. Next lesson we will move on to the mechanical properties of materials. Thank you.